Yeah, my name's Tony, and I'm working, as Maria Jose was saying, with her as a colleague in the food packaging group at the Institute of Food Agrochemistry and Food Technology. And I was asked to give a talk about innovation in food packaging. And of course, innovation in food packaging can be many, many things. It can encompass so many aspects, and also our focus actually in only a couple of them. Innovation can be about changing shape and design of the packaging materials, and we have so many different shapes and designs available. Innovation can be about new manufacturing technologies, so we can innovate in creating more efficient processes or more cost-effective processes, or maybe more environmentally friendly processes. But of course, innovation is also creating new packaging materials. And for example, this can be new high barrier materials that can be achieved through blends or multi-layered systems. And as an example, we can drink beer in plastic bottles without altering its aromas and its taste for many, many days. All through smart or active packaging strategies, which have been a topic of innovation since the turn of the century and the beginning of the century. And these strategies continue to be applied and developed. I will summarize them in a while. But when it comes to recent years, I would say that the biggest innovation efforts, both research and industrial efforts, are devoted to the development of new bio-based and biodegradable materials, the so-called bioplastics. But what is implied with these terms? What is smart packaging, or what is active packaging? What is a bio-based, biodegradable polymer, compostable polymer? I will go through these terms, and I will try to give you some examples. So a smart packaging is a packaging that knows. It knows about the contents of the inside. It's not just a mere container. And is capable of carrying out intelligent functions. Sometimes it's just communicating about its contents, but it could also sense or record or trace or detect changes happening inside the package, or even apply some scientific logic. Although not actively interacting with the package contents, it provides information, or it can warn about possible problems, which of course facilitates a lot decision making by either, Can you see now?
Yes.
Okay, so
yes.
it can enhance
yes, we can.
Safety, or so indirectly, if you facilitate decision making by either consumers or producers, then you are indirectly enhancing safety or extending the shelf life, or of course improving the quality. So for example, RFID labels, which can get really tiny, as you can see in the can, or QR codes, give only static one-time information, but of course can be considered smart packaging as well. Then we find temperature or temperature time indicators, for example, from quite simple leucodyes or thermochromic inks that inform about changes in temperature. For example, if your beer is cold enough, or if your cup of tea is hot enough. And these sensors can get a little bit more accurate in freezing indicators or cooking indicators. Then we have combined time temperature indicators, which give information about breaks in the cold chain. So when a specific time temperature combination is reached, then the color changes and informs the consumer or the producer about the spoilage of the product, or the significant break in the cold chain. We also have direct spoilage indicators, which are capable of continuous detection of contamination. Sometimes they might detect sulfur or amine volatiles, for example in fish spoilage. And these can be even included in barcodes. So the barcode gets unreadable when the color changes and the product is spoiled. And we also find other quality indicators. For example, oxygen saturation indicator, which can be visually inspected with a specific chromogenic detector. So we see how much oxygen is actually on your package, and if it surpasses a certain amount, then it wouldn't be okay for consumption. Then we have indicators for ripening. So the sensor changes color through the fixation of specific aromatic compounds. So then the color changes from, in this case, we have two products, a Belgian product, and then the other one is from New Zealand. So it goes from red to yellow through the different ripening stage and formation of aroma compounds. Then we have indicators of moisture changes, for example, cobalt or copper chloride indicators that change when they are saturated with moisture. And of course, there are myriad forms and trademarks of these smart packaging technologies, which are very famous in the US and Japan and widely used all throughout Asia and the Americas, also Australia and New Zealand. Not so much in Europe, though. And so then I will try to explain what active packaging is. So according to European Regulation 2009, active packaging is a system which deliberately incorporates components that would release or absorb substances into or from the packaged food or the environment. So we're adding a substance to the package, which is actively changing the composition of the inside in order to either preserve the quality or increase the food safety or extend the shelf life or decrease food losses, reduce food additives, and of course we are having a new product, so it's also used as a marketing tool. Active packaging relies on systems that either retain or eliminate food products or systems that release compounds to food, and also self-heating or self-cooling devices are also considered active packaging because they of course change the physical chemical properties of the inside. So in the active packaging we have an active substance that can be either incorporated in sackets and pads which are placed inside of the packages, or can be directly incorporated into the packaging materials, and each of them has different pros and cons. So for example, if you see about the different sackets, of course having a strange thing in your food package can cause rejection by the consumer, but then incorporating it directly into the packaging material usually means having an inner coating, because of course if in many cases the active substance might not leach enough from the packaging material or change the physical chemical properties of the package itself. Among the most common applications we find oxygen scavengers. So they can be either incorporated in sackets or in the inner coating, so that they help or promote avoiding rancidity or discoloration changes or andesite odors resulted from oxidation. We also find carbon dioxide generating systems, which find much use in meat and vegetable packaging. Then we find ethylene scavengers, which absorb ethylene produced by fruits and thus slow down ripening and senescence. We have humidity controlling systems in different shapes, or active releasing systems that release either antioxidants or antimicrobials or specific flavor or other compounds. So that's about what smart packaging and active packaging is. Our group has been working traditionally a lot with them, but lately in recent years I think most research and innovation focuses a lot on the search for bioplastics, so I'll focus a little bit on that. As you know, most packaging materials are actually polymers, and as you see in the graph, the green is polymer, but also multi-layered systems, which is the blue one, contain plastic polymers here and there. And that's no wonder, because they are used for a reason. They are very versatile, both in the processing methods and in the shapes and the different formats that they have. They are very cheap, they are very light, they have good optical properties, they're printable, and you can integrate the whole packaging in your production line. So it's very convenient. But there is one big disadvantage: petroleum-based polymers are not renewable and do not degrade in nature. So they produce high volumes of residues. Even in developed countries, such as in the EU, only a fraction is actually recycled, and that only into lower value materials. So they're not actually reused for the same purpose. Most part is burned, causing pollution, or dumped in landfills, where it accumulates, causing a huge global problem. As an example, we have the Great Pacific Garbage Patch. Well, governments don't directly face this problem that much, but a lot of pressure is on them lately. So they are forced to do changes, and lately they are saying that they do changes. So they say, for example, that they will restrict next year the single-use plastics. And of course, the consumer demand for environmentally friendly alternatives are boosting innovation in these sense towards the bioplastics. So what are bioplastics really, and what term would we use? Bioplastic or biopolymer? It doesn't really matter, because bioplastics are biopolymers. Although strictly speaking, a biopolymer can be any natural compound made out of monomer units. So DNA is a biopolymer made up of nucleotides, and proteins is a biopolymer made up of different amino acids. A plastic can be regarded as a bioplastic if it is either bio-based, biodegradable, or both. Bio-based means it does not come from petrol, so it comes from renewable resources, resources which can be restored by nature or human action. While biodegradable means that it degrades by naturally occurring microorganisms. And composting is a human-driven biodegradation, so a compostable plastic is a plastic which is biodegradable at certain composting human-driven conditions. So bio-based does not really equal biodegradable. Of course, if we think about natural sources, about wood or about cellulose or about any other natural source of biopolymers, then they are both renewable and biodegradable. But there are some examples where both features do not actually combine. For example, we have PBS and PCl in the upper left side of the graph, which are derived from petrol, but are fully biodegradable. And then on the opposite side, on the lower right side, we have biopolyethylene, biopolypropylene, and all the different biopolyolefins and biopolyamides, which are not derived from petrol, they are derived from bioethanol. So they are from renewable resources, but then they have exactly the same structure and properties as their fossil-based counterparts, so they are not biodegradable. And based on the origin, bioplastics can be derived from either natural origin, biotechnological, or synthetic origin. So they could come from agricultural sources, proteins from animal, like silk, collagen, whey, from plant source, zein, soy, gluten, polysaccharides such as starch, lignin cellulose materials, wood straw, chitin, chitosan from crustaceans or fungal biomass, and pectins or gums from the primary cell wall of plants or exudates. Then we have microbial sources, for example, bacterial cellulose or polyhydroxyalkanoates, PHAs, which we will talk for afterwards. And then we have biopolymers from biotechnological origin, for example, polylactides as polylactic acid. Of course, we have bioplastics from synthetic origin if they are either from renewable resources like the bio-based polyolefins and polyamides, or they don't come from renewable resources but are biodegradable like PCl or PBS. As for 2019, bioplastics are only less than 2% of the whole plastic production. And if you see the graph on the left side, half of all bioplastics produced are actually non-biodegradable. You see the green, blue, gray here. Furthermore, we have PBAT, which is a copolymer produced from oil and not fully biodegradable because of the terephthalate contribution. So actually only a third of all bioplastics are fully renewable and biodegradable. The market drivers of these are mainly starch blends, followed by PLA. And far behind, we have the PHAs, which is make up only of about 2% of the whole bioplastic production. Of course, market is rising, and this could change very, very quickly because legislation restrictions might come, and then if they are enforced, then everything, the whole scenario might change. So we have starch-based bioplastics which dominate the market, and that's because they are economically competitive. So the feedstock is cheap corn, potato, wheat, or rice starch, and it's relatively easy to process once the conditions are set up. Of course, it has some drawbacks. It needs additives such as plasticizers, a lot of it actually. It could come up to 50%. It also needs water and nucleating agents to reduce the melting and the glass transition temperature. And still, that means that the mechanical properties are actually much inferior to petrochemical properties. We have also retrodegradation, so it becomes again brittle, low resistance to solvents and oils, and sometimes too much rapid degradation. Of course, this can be solved by blending with other polyesters, and that's what's actually done. Or you can then put reinforcing fillets, of course, at a much higher cost. Sorry, it's difficult. I don't see the whole screen with this GoToMeeting, so I have to switch here and around. We have many different trademarks for thermoplastic starch. Most of them are usually blended, as I said, with different polyesters or other polymers to improve the different properties. And the application of thermoplastic starch is quite limited. We find thermoplastic starch in plastic bags. So if you go to your vegetable section in your supermarket, you might find these 100% compostable plastic bags. The second driving force in the bioplastic sector of renewable and biodegradable materials is PLA. It was actually the first mainstream polymer to be made from renewable resources. And it's fully biodegradable, made up of lactic acid building blocks. So we start from corn. From corn we get starch. Starch we ferment, first to glucose and then to lactic acid. And lactic acid, we do condensation to oligomers, take the lactite, and then ring opening polymerization to PLA. The physical chemical properties of PLA are actually very similar to PET, so that's good. And they have actually quite okay thermal properties and good processability. The biodegradability I would regard as amenable because it does not biodegrade so quickly in, let's say, realistic environments, but it's very fastly compostable if high temperatures are reached. And that's actually very practical because it decomposes when you want it to decompose. Of course, it has other drawbacks, for example, a limited barrier properties compared to benchmark PET, low thermal stability, and it's also too brittle for many applications, so it has to be blended. A common applications for relatively pure PLA is single-use plastic cups and glasses. So if you go to the supermarket and buy these ones, you may find that it says, please do not store hot drinks inside. And that's because of the low thermal stability, so that's a big drawback. Sorry, just skip this one. The main producer is NatureWorks, but we have other producers in Europe and Japan. And they can come either from corn, as I said, but also through lactose from whey. And we have many different trademarks as well, mostly combining PLA with other more ductile and flexible polymers for, let's say, widening the range of applications. And last, I want to talk about PHAs, which is marginal compared to starch-based plastics, but still consist about 2% of the whole bioplastic production. PHAs are polymers produced by bacteria under limiting conditions as an energy reserve. So structure and properties actually depend on precursor substrates, and that can be good if you want to tailor the properties. So that gives a lot of play for research purposes. But of course, this advantage can also be a drawback. It has quite okay thermal properties. It's suitable for low and medium temperature processing, but not for high temperature. It has very good biodegradability, so it actually degrades fast in natural environments, in soil, in viral environments, and of course through composting. But it has a very narrow processing window, so it degrades upon two very high temperatures upon processing, and it's also excessively brittle for some applications. It's also sometimes dependent, the properties are sometimes dependent on the relative humidity. And I think most of all, it needs complex raw materials and bioreactor needs, which increases the price. Several trademarks for PHAs, Miral and Biomer, and the applications are many and not only reduced to food packaging. We have many applications also in the biomedical or pharmaceutical industry. A common food-related use is cutlery, so with this very typical white, opaque, slightly brownish color that you see in the picture. Well, as you can see, the range of use of the different renewable and biodegradable plastics is, to this date, to those that are being applied in the market, is quite narrow. Of course, lots of research has been done about it, and many possible solutions have been actually found, but they have not found that way into the market, possibly because of the increase in the final price, and that makes them usually impossible to compete with conventional plastics. So research and innovation goes on to find the perfect compatible blend with complementing thermomechanical properties for wide use and of course very low cost. At our research group, we are engaged in different national and international and privately funded projects focusing on the valorization of different biomasses. So we have marine biomass or agricultural waste in order to transform a seemingly useless waste into a really economic, affordable food packaging. But that might be the topic of another talk some other day. I think it's already past, so I want to thank you for your attention. I hope you learned something about different terms related to active smart packaging and bioplastics.